not many people are coming to lab, so if you want to come, whether you're Group A, Group B, or Group C, please do come to lab and take part in that, and we'll go over it, or I will personally go over the lab with you, okay, the lab on Hess's Law. It's also what I'm going to be talking to you guys about in today's lecture. All right, so another housekeeping assignment, housekeeping announcement is I got an email from Clutch Prep, so they want you to do that Clutch Prep drills. Right, someone has already told me that they don't like coming once a week. They want to come, twice a week or whatever. So use those Clutch Prep. Okay, that's why I got them. That's why we as a department got them. So use them. That will help you. And she expressed concern about Chem 2, so that should help you get squared away coming to my lecture, watching the videos, and then using that online tutor, Clutch Prep. Having said that, I think there's like 8 or 9 A's in the course, so for the most part, people are doing well. Also, I want you guys to work on your Chapter 6 homework, so make sure you do that and upload your work, and I'll give you 10 points for that. All right, today is the 6th of October. A couple of things I want to mention. Okay, start working on quiz 3. Okay, I'll have your quiz 2 graded. I already graded one section. I'll have the other section, your section, graded. Work on that. And Clutch Prep. Okay, I think some of you have not done that, so it's part of your grade, participation points. I'll just give everyone the points, but they have to do it, right? That's the thing. You have to go ahead and watch the videos and do the little sample questions. Work on homework 6, and labs is going to be on Hess's Law. Okay. I think you guys did really good. So on that lab, and also Boyle's Law. Okay, this is how it's going to have to be until this pandemic is over, until we can get to 3 times a week class, unfortunately. All right, Chapter 6 has to do with energy. Okay, energy. So what do you guys think of when you think of energy, the term energy? You have a lot of it, or a little of it? Little of it? Okay, from a chemistry standpoint, okay, there's all different types of forms of energy. Okay, you can have radiant energy, thermal energy, you can have chemical energy, okay, potential energy, kinetic energy. Okay, we have all sorts of different manifestations of energy. Okay, nuclear energy. Okay, this was mentioned in the morning section, the Monday, Wednesday, Friday class. There can be mechanical energy for the mechanical engineers. There could be gravitational energy if you're looking at the planets, what holds them together instead of crashing towards one another. So there's different manifestations of energy. One thing I want to tell you about all of these forms of energy is that they could interchange from one to the other. Solar energy, they can interchange from one form to the other, but they cannot be created and they cannot be destroyed. They can just shift forms. So the first point I want to tell you is that energy cannot be created or destroyed. It just changes form. Okay? It just changes form from one form to the next. Okay. All right, I also want to do a reaction for you. Okay, nothing special, nothing too complicated, but I'm going to perform a neutralization reaction, which is something that you actually did in the lab, which was the aqueous reaction. aqueous reactions lab, okay, if you remember that. But a neutralization reaction is basically a reaction between a strong acid and a strong base. Okay. The strong acid is 100% source of H+, that's a proton. And the strong base is 100% source of OH-. Okay. And all of this leads to water. So in this beaker, okay, I'm going to have my strong acid, which again is a 100% source of protons. I'm going to have my strong base, which is 100% source of my OH-. Okay? And all of this is housed in this beaker. Okay, a beaker. Let's put this beaker here in green. So let's do this reaction. Let me see if I can switch here. All right, so what I'm going to do is I'm going to do this reaction, and then I'm going to monitor the temperature, right? So I'm going to have the temperature. So the first thing I'm going to do is put in 6 molar of NaOH. Okay, 6 moles per liter. Yeah, that's pretty concentrated. So let's do that. Let's pour some of it in. Okay, I'll pour about 20 milliliters in. Okay, what I have here is just a temperature probe. It just monitors the temperature. It's like a thermometer. Okay? It just monitors the temperature. So I'll put this in this beaker here. So nothing too crazy, I hope. Okay. So 20 milliliters. So NaOH is what we're going to call a strong base. Okay, NaOH is a strong base, so it's a 100% source of OH-. Okay, let's just monitor the temperature. The way I'll monitor the temperature is by clicking on the collect sign. Let's just start brand new. All right, so it's monitoring the temperature, and right now I have sodium hydroxide, actually sodium ion and hydroxide ion. And it's monitoring it, monitoring it. Okay, monitoring the temperature. Looks to be about 20 degrees or so. All right, so now let's mix something in there. Okay, so I already have, can you guys see this? Are you okay? Can you see it? Well, we just need to focus on that. Okay, so I already have my NaOH in there. Can you see this, Courtney? Right. I'm going to add 6 molar HCl, moles per liter, and that's pretty concentrated. Okay, this is 100% source of H+. Okay, 100% source of H+, 100% source of OH-. Okay, let's mix this up and see what happens to the temperature. Okay, so what do you think is happening to the temperature? Temperature is going up. Okay, the temperature is going up. Okay, that is in essence a neutralization reaction. So where do you think the heat is going as the temperature goes up? Okay, it's going to. Can you feel this?
Yeah, it's warm.
It's warm. Maybe not as warm. You kind of felt it? Yeah. Okay, it does feel. Actually, if you feel it with your palm, it's warm. And as the temperature goes up, okay, what has happened now? Where has that heat gone? It once was at the beaker, right? Where did it go now? Well, first of all, okay, you three know that the thing is warm. Okay, it went to warm the beaker. Then where did it go? It went to this room, and then from this room, where did it go? It went to the school, and over time, where will it go? It will go to North Carolina, and over time, where will it go? United States, and over time, where will this heat go? A planet Earth, and over time, where will this heat go? The universe. So, in essence, yeah. Okay, so this heat, which is a form of energy, is going to dissipate. Okay, first it goes to the beaker. You wait an hour, it goes to this room. Wait another hour, it goes to the school. Wait several days, it goes to the state, and then the country, and then the earth, and then the universe. So really, you can define a reaction in two ways. One is the system, and the other one is the surroundings. So let's go back to our diagram here. Okay, so we have our strong acid, which is HCl. Okay, we also have Cl minus here and Na plus, sort of the spectator ions. Okay, what I want to tell you guys is that we can define this reaction in two parts. Okay, one is called the system. Okay, which is just all the reactants, okay, reactants and products inside the beaker. Okay, that's the system. And then everything else, including the beaker. This is a big point here. Everything else, including the beaker, because you guys saw it felt warm, right? Everything else, including the beaker. Okay, we're going to call that the surroundings. Okay, the surroundings. So system and surroundings, okay? That includes the beaker, but eventually remember, okay, from the beaker to this room, to the school, blah, 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 all the way out, all the way out, all the way out, all the way out, all the way to the universe. So really, you can go all the way to the universe. You can define your surroundings as the universe. Really, you can. Okay. So what we have here is sort of a communication, okay? Communication between the system and the surroundings. They're in communication with one another. Okay. Right now, this is in communication with the air. And this is in communication with the universe. Okay, it is. In communication means air can come out, air can come in. I can blow on it. I can do stuff. Okay. But they're in a communication. Right? You can generate a system that's isolated. You can generate a system that's closed, where it's not so much in communication with the surroundings. But right now, what you see there is pretty much an open system. Okay? It also includes the beaker. Okay? It also includes the beaker. It also includes the beaker, but really when we talk about the surroundings, we're really talking about essentially the universe, because the heat that's evolved is going to go to the universe. All right, so we just had a neutralization reaction there. You didn't see much of an explosion. You didn't see much of anything. You did not see it precipitate, but we did see heat. Okay. Okay, which is a type of energy. Where does that heat go? Okay, the heat dissipates, right? Okay, the heat dissipates. Heat is a type of energy that is different than nuclear energy, mechanical energy, gravitational energy. It's different than all these types of energies because what's the difference? It just goes to the universe. So heat is a type of energy that dissipates. It cannot be harnessed. Cannot be captured. All these other forms of energy can be captured. Okay, all the biochemists and the biology majors may know that chemical energy in our cell comes in the form of ATP. Okay, you can break open an ATP, create energy, and make, release energy. So, these are energies that can be harnessed or captured or utilized. Unfortunately, heat is not one of those. However, this reaction, this neutralization reaction, does produce heat as a product. Okay, a couple of things here. Heat is going to go by lowercase q. Okay, lowercase q. Right, and then let me just tell you briefly about the units. The units are going to be in joules. Okay, J, and that's going to be joules. Okay. Units of heat, which is a type of energy. Okay, I can also say unit of energy. Okay, so where you'll see this in your problem set is going to be joules over mole over kilojoules over mole. Okay, so those are the units typically of energy. Okay, so heat is lowercase q, and it's joules per mole or kilojoules per mole, and that you will see, in our chapter, in this chapter. All right, so this reaction produces heat. Okay. How do we know it produces heat? Because what happened to the beaker, Tiana? Didn't it turn warm? Do you remember? Let's see if it's still warm. Not that warm, but it produced heat. Okay. The beaker turned warm. Okay. We can call this type of reaction where the beaker turns warm, which is a transfer of energy, heat energy. Okay. We can call that an exothermic reaction. Exo meaning outside. Exo means outside. The beaker turned warm. Didn't it? Right? The beaker turned warm. Okay, how do we know the beaker turned warm? Well, we felt it. You guys felt it. But also, once... Right at this point, I added the HCl, and look what happened to the temperature. Okay, it went up. Okay, and then what happened? It started to cool down. Okay, because this is an open system. Okay, air and everything from the outside started to mess around with it. But right at this point, when I added the HCl, boom, the temperature skyrocketed. Where did it go? It went to warm the beaker. It went to warm the beaker. Okay, we're going to call that type of reaction exothermic. Exo meaning outside. Okay. What is being transferred here? Okay, heat. Okay, the type of energy that we cannot capture. It warmed the beaker, then it warms the room, then it warms the school, then it warms blah, 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 blah. It warms all the way to the universe. Right, so a neutralization reaction is really your prototypical example of an exothermic reaction. And the type of energy that's liberated is heat energy, and heat is a product in this chemical reaction. Heat is a product. Okay, we can contrast this with an endothermic reaction. And And I'll just give you, I don't know a specific endothermic reaction, but I'll just tell you in an endothermic reaction, you don't take heat, you don't give out heat. What do? You take in heat. From where do you take in heat? From where? From the surroundings. Okay. So this would be an example of what we're going to call an endothermic reaction. Endo meaning inside, so it's taking it in. Okay, the system, which is just the chemicals inside this beaker, the system is taking heat energy in. Where is it taking it in from? It's taking it in from the surroundings. So this would be an example of an endothermic reaction. So we have exothermic reaction and endothermic reaction. What's being released or taken in? Heat, which is released or being taken in. Okay? Endothermic versus an exothermic reaction. So how do you know if the reaction is endothermic? Well, I added acid to this base and the beaker turned warm. Okay, what will happen if this reaction were endothermic? What would the beaker turn? Not warm, but cold or cool, yes. Cold or cool. So this beaker would turn cool. Here, the beaker would turn warm in an endothermic reaction. So we have our system, which is just all the chemicals inside, the surroundings, which is everything else, including the vessel, including the beaker. A couple of other points I want to mention here is for an exothermic reaction, we have the heat of the system, and then we have this heat, lowercase q, of the surroundings. Okay. For an exothermic reaction, the heat of the system, okay, it's giving away heat. Okay. Exo meaning outside to the surroundings. Okay, the value of the heat, that lowercase q, is going to be negative. Okay. Negative joules per mole, negative kilojoules per mole, whatever. It's going to be negative. What do you think the sign of the surroundings would be for an exothermic reaction? Okay, remember, energy cannot be created nor destroyed, so what will the value be? Okay, it will not be created, energy cannot be created, cannot be destroyed. It's going to be the same value, but what sign? Positive. Okay. Okay, so this is the scenario for an exothermic reaction. The system is going to be negative. The surroundings, which is the beaker, room, universe, okay, it will have the same value but opposite sign, and that's going to be positive because energy cannot be created nor destroyed. It just changes forms. Okay. What about an endothermic reaction where heat is taken in? What would be the sign of the system and what would be the sign of the surroundings? Heat of the system, which is just the reactants and products, what will it be? Okay, it will be exactly the opposite. Okay. Okay, these guys, endothermic and exothermic, are opposites of one another. So this would be positive for the system because it's taking stuff in, taking it in. The surroundings, what are the surroundings doing? Okay, the surroundings are giving heat energy to the system, so the surroundings are going to be negative. The sign will be positive for the system, sign would be negative for the surroundings if you're talking about an endothermic reaction. So heat flow between the system and the surroundings. Okay. And let's also talk now about work. Okay. So we have heat, and then we have heat energy, which is dissipated, cannot be utilized. And then there's work energy. Okay, what do you think work energy is? Okay, what do you think about when you think of work? Okay, you think about this class? Okay, you think about your job? What do you think about when you think of work? Okay, here we have energy. First of all, it goes as lowercase w. Here we have energy that can be harnessed, that can be captured. Okay, so while heat is kind of useless, though I hate to use the word useless, useless energy, work is useful energy in the sense that it can be captured or it can be harnessed. Can be captured or can be harnessed. Okay? Captured and harnessed. So all of these things, all of these forms of energy actually can do work. Okay? All of these forms of energy, radiant energy, thermal energy, chemical energy, you see the ATP molecule. You see the ATP molecule. If you break an ATP molecule, okay, it has enough energy to actually take an endothermic reaction and move it forward, because remember, endothermic reactions require energy. So ATP can do work for the cell, okay, if you are a biology person. Adenosine triphosphate, but you don't have to worry, it's a biology molecule. You never heard of it? Oh, wow. Okay. I think you're computer science, right? Yeah. That's fine. So, but it's a molecule that stores energy. You can think of it that way. Yeah, that's a good question because it's nice to have computer science majors take the class, so thank you. This type of energy can do work, okay? Something that can be captured, harnessed, something that's useful for whatever, okay? That whatever the system wants to do or whatever you want to do, it's just energy that doesn't dissipate. It's not energy that goes to the universe, which is usually what heat energy is, okay? And so that's the difference between heat and work. All right, so heat can be exchanged between the system and surroundings. Okay, the same thing you can say about work. Okay, work between the system and surroundings. Work between the system and the surroundings. So for that, I'm going to need a volunteer. My ruler here. Do you want to come, Marie? Help me out here, dear. Just in here. You be the surroundings, I'll be the system. So pretend I'm the system. okay, what did we say the system was? Just the reactions and reactants and products. And she's the surroundings, Marie is, which is even the beaker, but really it's everything else, right? Okay, we're talking about work. Okay, we're talking about work. We already talked about how heat can be exchanged between the system and surroundings. Okay, now I want to talk about energy that is in the form of work. All these energies can do work, okay? So this is how we're going to do it, or this is how you want to think about it this way. So I am the system. I'm going to push you gently. Okay. I am the system. I do work on the surroundings. Okay, so that way. Okay. Work done by the system. By the system. Okay. On who? Okay, on the surroundings. Okay. So work done by the system. Okay. On the surroundings. Work done by the system on the surroundings. I, the system, am going to be negative. I'm doing the work. My value is going to be negative. Okay, what will Marie, the surroundings value be?
Positive.
Same value, but positive. Okay, so work done by the system on the surroundings. Okay, I am negative, and surroundings are going to be positive. Work done by the system on the surroundings. Do it gently on me. Don't take your vengeance on me. I didn't create your business. All right, we'll do the opposite now. Okay, work done by the surroundings on the system. Okay, work done by the surroundings on the system. Okay, the surroundings do the work on whom? On the reaction, on me, the system. So the surroundings are going to be negative, negative. Okay, what will the system be? Same value but positive. Okay, same value but positive. So work done, one more time, work done by the surroundings on the system. Okay, system positive, surroundings negative. Work done by the system on the surroundings, by the system on the surroundings. Okay, system is negative, surroundings are positive. All right, heat. Heat released from the system to the surroundings. Heat released from the system to the surroundings. What's the sign of my heat? Negative or positive?
Negative.
Negative. What's the sign for the surroundings? Positive. We call that an exothermic reaction. See? Okay. It's releasing energy, heat. It's releasing heat to the surroundings. That's an exothermic reaction. Finally, the flip side, okay, heat released from the surroundings to the system. Heat released from the surroundings, Marie, to the system. The surroundings are going to be negative in value. The system, the reaction, is going to be positive in value. That is an endothermic reaction, endothermic. Taking in the system, the reaction, taking in heat energy. So there's work exchange between system and surroundings. There is heat exchange between system and surroundings. Heat, unfortunately, just goes away. Work, yes, that is something that can be captured. Okay? Whatever engineering, computer science, whatever, biology, that type of energy, mechanical engineering, that type of energy can be captured, can be harnessed. Thank you so much. I appreciate that. I think she did a great job. I think I'm a big fan of her as a student. All right, so let's write this down here. All right, so let's review all of this here. We have work done. Okay, I'm talking about work, not heat. Work done by the system on the surroundings. Okay, work done by the system on the surroundings. Okay, the work function will be negative for the system, and the surroundings will be the same value but opposite in sign, positive. By the system on the surroundings. I'm negative, the surroundings will be positive. Okay, another scenario is this. We have work done by the surroundings on the system. Okay, by the surroundings on the system. By the surroundings on the system. Okay, in this particular scenario, the work function for the surroundings is going to be negative. Okay, the value will be negative. And the system is going to be positive. All right, so that's work. Okay, let's talk about heat. Okay, work is lowercase w, useful energy. Heat, useless energy. We have heat released. Okay, this is lowercase q. Heat released from the system to the surroundings. Okay, that's when our beaker turns warm, a neutralization reaction. Heat released from system to surroundings. Okay, I'll just use that as surroundings just to. From system to surroundings. Okay, the value of our heat is going to be negative. The value of our surroundings is going to be positive. Okay, I want you guys to recognize this as being an exothermic reaction. Exothermic, going to the surroundings. And then we have our last bit here. You see, pluses and minuses are going to be important in this chapter. We have heat Q released from the surroundings to the system. Okay, from the surroundings to the system. Okay, in this case, the heat of the surroundings will take on a value that's going to be some negative number. The system will take on a value that's the same, but it's going to be positive in value. And I want you to recognize this as an endothermic reaction, a reaction that requires heat. So it's going to be on the reactant side. This is heat energy is energy that cannot really do anything. Unfortunately, it just goes to the universe, the surroundings. Work energy is all these different types of energies that can do stuff, okay? Or hopefully be captured in one way or another. Okay, talking about energy here. All right, let me just also say this kind of a source of confusion in previous years. So let's say I have a beaker with some chemical here. Okay. Everything outside is the surroundings, right? Yes, everything around it is going to be the surroundings, including the beaker itself. So let's say I cool this. If I'm cooling this, okay, what's going to be the value of my heat for the system and the surroundings? Okay. Let's say I cool this. Okay, let's say I heat this. Okay, what will be the value? Okay, what happens if this cools? Okay, where is that energy going? When this thing cools, okay, it's cold now. Okay, where is it going? To the surroundings. Okay, so if you're cooling something and it's giving energy to the surroundings, what's the sign of our system? Negative or positive? It's giving it to the surroundings. It's going to be negative. Okay, yep. So when you're cooling something, the system is negative, so obviously the surroundings, what do the surroundings do? You think the universe says, hey, I don't want this heat, go back to the beaker? Okay, never does that. Okay, the surroundings just take it. The universe doesn't heat back up the beaker. Okay, let's say you heat this. Okay, what am I doing? Okay, I'm doing voodoo on this. Okay, I'm trying to heat this. Okay, what does that mean for the system? Okay, it's taking in heat. Okay, whatever I'm trying to do. Okay, so what will the sign be if I'm heating something? Okay, it's positive. Okay, if you're trying to heat something, okay, you're adding energy, you're adding something to the system. Okay, what is the surroundings doing? The surroundings are giving some. You're heating it, so what are you doing? The surroundings are giving energy to the system, so it's going to be the same value but minus in sign. Okay, so that's how you want to think about that. Differences between heating and cooling something in terms of heat. Okay, heat. Because when you're cooling something, you're taking away heat. When you're heating something, you're adding heat. What's happening to the reaction? What's happening to the universe when you're doing these two things? I also want to tell you one thing, 1 joule, okay, 1 joule, which is the unit you're going to see a lot in this class, actually is derived, it's 1 kilogram meter squared over second squared. Okay, so just so you know, you do not need to memorize this. It's not something for the exam. But for more advanced students, this is derived from the SI base unit kilogram, SI base unit meter, SI base unit seconds. Right, that's what 1 joule is. Joule is going to be the unit of energy here. All right, there's different types of systems here. So Right, there's different types of systems. You can have a system that's open. Okay, when we say an open system, this is an example of an open system. This was formerly the site of a neutralization reaction I performed. Now it's just a cold beaker with some liquid. Okay, so there's been an exchange. Okay, an exchange of heat. There's an exchange from the surroundings. Okay, all of this stuff is the surroundings. All of this area. Okay, but you can enclose yourself from the surroundings. You see, you can enclose yourself. This is a closed system. Okay, so the only thing that can get exchanged between the system and the surroundings is energy. Okay, and then you have an isolated system where there's no exchange between the system and surroundings. Okay, the system and surroundings have no exchange. No exchange of heat, no exchange of water vapor, no exchange of mass. Have you guys heard of an adiabatic chamber? Have you heard of that? Adiabatic chamber. Okay, so that is an example of an isolated system. Adiabatic chamber. So it's some container where it's totally isolated, no pressure changes, no volume changes, and completely in a chamber. Okay, so that would be an example of an isolated system. All right, exothermic versus endothermic processes. Just want to hit home the message that if your heat, in this case the energy that I'm talking about is heat, if it's in the product side, okay, we're talking about what's called an exothermic reaction. Okay, exothermic. In other words, this releases heat. And so please don't get this, don't miss this on any exam or quiz. If your heat energy is required, then if it's required, it's part of the reactant, and that is an endothermic reaction. Okay, so one side it's a reactant, endothermic, the other side it's a product, okay, exothermic. We're going to see this term a lot here. Okay, this term is called delta H. Okay, delta, this is the symbol, the Greek letter delta. Okay, and it means change in. So delta H is actually what we're going to call the change in enthalpy. Enthalpy is that H term. Okay. Change in enthalpy. 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 Enthalpy, in the strictest definitional sense, means heat flow. Heat flow from reactants to products, or heat flow from products to reactants. Heat flow from reactants to products, or vice versa. So we're going to be talking about next week what's called the delta H of a reaction, okay, which is the enthalpy of a reaction, okay, heat flow. So another important point here, okay, the delta H of a reaction for an endothermic reaction is going to be negative, okay, exothermic reaction, the delta H, which is the change in enthalpy, is going to be negative. Units, they can range anywhere from kilojoules per mole. In your textbooks, you'll also see joules per mole. And the next important point I want to tell you guys, the delta H change in enthalpy for a reaction that is endothermic. A reaction that's endothermic will have a positive value. Okay? Reaction that's positive value for an endothermic reaction, the delta H. Delta H being change in enthalpy. Again, units you're going to see when you do your homework or read the textbook, kilojoules per mole, joules per mole. So enthalpy. And its basis in terms of what's positive versus what is negative. All right, kind of the same thing here. Okay, an exothermic reaction, just recognize energy, heat is flowing out. And in an endothermic reaction, heat is flowing in. Okay. That's all this is saying in its own complicated way. I'm going to define to you now what's called a state function, and I'm going to define it to you, but I'm not going to test you on it. It's not on the exam, but definitely for the engineering majors, maybe the hard sciences, you will encounter state functions a lot in your math classes. Delta H, which is enthalpy, is a state function. Okay, so what is a state function? I'll just lecture on it briefly, and that will be that. So let's say we have a reaction of A going to B. Okay. And I tell you that this has a change in enthalpy, the enthalpy of the reaction, delta H. We'll just say it's minus 100 kilojoules per mole. Okay, the minus sign should immediately clue you in that this is an exothermic reaction. Okay, so delta H is what's called a state function. So I have A to B minus 100 kilojoules per mole is my delta H. Now how do I get from A to B? Do I do it single shot? Do I have A go through intermediate C? And then goes through intermediate D, which in turn goes through intermediate X, which in turn goes through intermediate Y, and then finally it gets to my final product B. So here, to get to my product B, I have 1, 2, 3, 4, 5 intermediaries. That's one route to get to B. The second path to get to B would be just straight single shot. Okay, maybe a third shot to get to B would be through another intermediary Q. Okay, we'll just call it Q. Okay, one intermediary step. Well, a state function is this. It doesn't matter whether I get to B single shot. It doesn't matter if I get through B through Q. It doesn't matter if I get to my final product B through C, D, X, Y, Z, and K. Okay, it doesn't matter, no matter what path or no matter what route I take, my delta H will always be minus 100 kilojoules per mole. That is to say, we don't care how we get to B. The fact we get to B, that's it, that's all. Okay, it doesn't matter what path we take. So in other words, this is really mechanism independent. That's what a state function is, and that's what delta H as a variable is. Okay, it's mechanism independent. So when you're doing your delta H problems for your homework and you see minus 100 kilojoules per mole, that's it. We're not concerning ourselves with how or in what way or what intermediaries or what mechanism. We don't care about how. Okay, we just know no matter how or what way, 100 steps or 5 steps, okay, that value is going to always be minus 100 kilojoules per mole. Okay, and that in essence is what a state function is. Again, important for engineering majors. All right, I'm not going to test you on this. Okay. All right, our abbreviations here, let's recap. We have lowercase q, which is heat. We have lowercase w, which is work. Okay, now we also going to have capital U, which is energy. Okay, some sort of total energy of the system. Okay. So the energy of the system takes contributions from heat, which we already know is Q. And it takes contributions from W, which we already know is work. Work is useful energy, heat is useless energy. Useless in the sense, I can't do anything with it, or we cannot do anything with it. Okay, so U is like total energy. Delta U is equal to Q plus W. Okay, we already went over this. So I think on the quiz or on the exam, you'll have this little box where you have to fill out what's positive and what's negative. So just really quickly, work done by the system on the surroundings. Okay, the system will be negative. The surroundings are going to be positive. Work done on the system by the surroundings, so the surroundings are going to be negative, the system will be positive. Heat absorbed by the system from the surroundings. Okay, by the system from who? The surroundings. So that's an endothermic reaction. The system will be positive, the surroundings will be negative. Okay, endothermic. Heat absorbed by the surroundings from the system. Okay, this is the beaker or the surroundings. The beaker is getting warm. It's taking it from the system, our reaction. This is your classic exothermic reaction. The system is negative. The surroundings are positive. This is your classic exothermic reaction. Okay, so we have work and heat, Q and W. All right. All right. Let me wrap up with the last page here. And then we can call it a day of lecture. All right, the key point of this page is to tell you guys that gases do what's known as pressure volume work. So gases, we're talking about gases, which was our last chapter. Gases do pressure volume work. So pressure we're going to call P, and then volume we're going to call delta V, change in volume. So look at this piston here with me. Okay, so here everything else is just called the surroundings. Surroundings. Okay. Now envision with me the gas expands. Okay, let's say the gas expands. So what happens if a gas expands from, let's say, here to here? Okay, the gas expands. Okay, what happens to the volume? Correct. The volume has gone up by this much. The volume has gone up by this much when the gas expands. So what do the surroundings do? Do the surroundings push back? No. You can't expand. Okay. If I remove my mask and blow, do the surroundings say, no, I don't want it? Will you blow it back at me? Okay, no. Okay. So what we're saying is that when a gas does work, it's doing pressure volume work. It's changed its pressure and it's changed its volume. Okay, so work. Okay, good energy. If this was a car, if you're a car buff, okay, you know this is happening with the pistons and all of that in your car. But if work is pressure volume work and we're talking about a gas, okay, what would the gas system be if it's expanding? Okay, I want to try to convince you that if the gas is expanding, okay, it's doing work against the surroundings, so it's going to be negative. The surroundings are going to be positive. This is for an expanding gas. Okay, that's what you see here. Okay, it's expanding. We got a new volume. The surroundings are, the universe doesn't do anything back at you, or I should say the universe doesn't do anything back at the gas. Okay, so the gas, if it's the system, remember the system is just the chemicals, it's going to be negative. The surroundings will be positive. This is when the gas expands. The surroundings just take it. Okay. We also say the gas is doing pressure volume work. Which is the key point here. Gases do pressure volume work. All right. If a gas doesn't expand, if a gas cools, or if a gas compresses, gas compression, this will be the opposite. Okay. All right, let's do a problem set here and then evaluate where we are in terms of our class. All right, a gas expands. Okay, a gas expands. Okay, blowing a balloon. Okay, a gas expands and does pressure volume work on the surroundings. Equal to 279 joules. So my question to you guys is, on the surroundings, is that the gas is expanding on the surroundings? So is that 279 joules positive or negative? Correct. It's going to be minus 279 joules. It will be negative. Okay, because it's doing it on the surroundings. The system is doing on you, Marie. I am going to be negative if I'm a gas. At the same time, it absorbs. Okay, it absorbs 216 joules of heat from the surroundings. So what do you think the sign is of that 216 joules, positive or negative, from the surroundings? Okay, I hope you all know it's going to be positive, okay, because the gas is taking it from the surroundings, taking it in our play. Marie was the surroundings. I'm the gas. I absorb 216 joules from the surroundings. So, okay, what is the change in energy of the system? Okay, so we're going to use this equation here. Delta U, change in energy of the system, is equal to Q, which is the contribution of heat, plus W, which is the contribution of work. Okay, the contribution of heat Q is going to be positive 216 joules. Plus the contribution of our work. Okay, remember, it expands and does it against the surroundings, against you guys, the universe. So that's going to be minus 279 joules. So 216 plus a minus 279. I'm getting minus 63 joules. Okay, minus. So there's something very important about that minus sign. Okay, what does the minus sign tell you? We're talking about work, okay, the energy of the system. So the minus sign tells you that, yes, it does two things. Number one, that this is exothermic, right? Did you say exothermic, Tiana? Yeah. Number one, it's exothermic. And number two, the system is doing work on the surroundings. That's point 2, which you missed. Okay, but point 1 is correct. The system is doing work on the surroundings. Okay, why do I say on the surroundings? Because of the negative sign. Why do I say exothermic? Because of the negative sign. System is doing work on the surroundings. That's the other important interpretation of the minus sign. So the minus sign, minus value, and the positive value in this chapter are going to convey very specific meanings, whether exothermic, endothermic, whether work is being done on the system by the surroundings, or work is being done by the surroundings on the system. Okay, positive and negative values are going to play a key role in all of that. All right, I think we will continue on next week. Do your homework, try to get ahead. Okay, watch those little quick videos, and I'll see you all. Do your clutch prep, work on quiz 3, and I'll see you all next week. I may see some of you in the lab also. So, okay. right, thank you guys for coming, and I'll have copies of these notes out for you as well.